guys, welcome back to TechDose, and in this video we will look at Make Lexicographically Smallest Array by Swapping Elements problem, which is from Leetcode number 2948. Let's now look at the problem statement. In this problem you are given a zero-indexed array of positive integers nums and a positive integer limit. In one operation you can choose any two indices I and j and swap the nums at I and nums at j in such a way that the absolute difference between nums I and nums j must be less than equals to limit. Return the lexicographically smallest array that can be obtained by performing the operation any number of times. An array A is lexicographically smaller than array B if in the first position where A and B differ, array A has an element that is less than the corresponding element in B. For example, the array 2, 10, 3 is lexicographically smaller than array 10, 2, 3 because they differ at index 0, which is the first position where 2 is less than 10. That is why this first array is smaller than the second array, right? Now let's look at the constraint before we look at any example. The number of items in the nums array is 10 to the power of 5, and that is why we cannot write an n-square algorithm, because that will make the total number of computations to be 10 to the power of 10. We should write something better than n square. Now all the elements in nums array and the limit value are within the integer range. Now let's look at an example for better understanding. But before that, let's try to understand lexicographically smallest in a little more detail. So let's say that your given elements A and B are given in the form of n string, or you can assume it as an array elements. So the first array A is having value 1, 3, 2. The second array B is having 1, 2, 3. So what we will do is we will compare each of them position by position from left to right, and if they are equal, I will be moving forward, and if they are unequal, the array in which the value is less, that array will always be smaller than the other array. So here B is less than A. If you look at the second example, in array A you have value 1, 3. In array B you have 1, 2, 3. So if you move from left to right matching, then you will find that the first element is matching, but the second element is not matching, and 2 is less than this 3. Therefore 123 or 1, 2, 3 B will be less than A. Now if you look at the third example, in this case the A value is 1, 2, 3, B value is 1, 2. So if you keep comparing the values, then 1 and 2 both are matching, but in the third attempt you will see that the array B do not have any item because the size is less, and that is why B will be considered to be less than A. So this is the meaning of lexicographical ordering. I hope this was clear. Now let's say that we are given an array and I ask you about arrange this array in such a way that you get the lexicographically smallest array. So what you will do is you will take the array and sort it in ascending order, because only if you sort it in ascending order you will get the lowest value on the leftmost side and the highest value on the rightmost side. Okay, so that the values are always non-decreasing. So this will be the lexicographically smallest array, right? But our problem in this case is having a limit constraint, right? So that actually differentiates it from being a general sorting problem. So let's now look at an example. In this case, let's say that we are given 5 elements with a limit value of 2. So the meaning of limit value was we can swap 2 elements only when the absolute difference was less than equals to 2. So if you just take an example and compare this 8, 2, can you swap this 8 with 2? Well, that will not be possible, because the difference, the absolute difference between 8 and 2 is 6, but the limit value is 2. The limit value is defining that the difference between them must be within the range of limit, less than equals to limit, but that is not possible, right? So that is why even if you want to place 2 here, maybe you will not be able to place 2 here, because the difference between this 10 and 2 are actually not within the limit range. Fine. Now if you have to solve it by the simplest possible approach, then you can think like a selection sort approach, where you will be picking the best option possible for this index 0. And how do you select the best option possible? Well, you fix this min index value. So this will be your minimum index, or let's say you call it the index I, and then you will be parsing using the j pointer right from index 1, or you can say from I plus 1 till the last index. Whenever you find that you have seen a smaller item and it is within the limit range, then you will do the swap. But in this case, the 3, even though it is smaller than 10, but the difference is 7, which is greater than the limit, therefore you cannot do the swap. Same thing goes for 5. But when it comes to 8, then it is smaller than 10 and within the limit, because the absolute difference between 10 and 8 will be less than equals to 2. So you can do the swap to get a lexicographically smallest number. Therefore, you will do it. It is a greedy algorithm, right? Now when you go to 2, then again 2, even though it is smaller than it, but the difference is more than the limit, so you cannot do the swap. So you have placed the best option in the first position, and now your I pointer will move to the second position, and now you will try your J loop right from the I plus 1th index till the last index and find out what will be the best placement here. You will find that 2 will be the best placement here and 3 will come here, right? And similarly, you can just perform the selection sort with the constraint of limit check. This will be the additional constraint to the code of selection sort. So I hope you already know selection sort, and if you do, then you know that the time complexity of selection sort is already order of n square. So this technique, the brute force technique, will take you order of n square time, and you know that the max value of n as mentioned in the constraint was 10 to the power of 5. So this will take 10 to the power of 10, and hence it will give you a time limit exceeded, as we already discussed. We should always write an algorithm in less than 10 to the power 8 computations. So we have to do something better here, right? So let's look at some observations which will actually help us improve the solution. So I will be giving you 3 different observations. Let's look at the first one. In this case, let's say that the given array is having 6 elements and the limit value is 2. So the elements form swappable group. This is always true. Elements will always form swappable groups. And how do you get the groups? If you look at this array, then you will find that 10, 11 and 8 will come in the same swappable group. Well, how do you know they are forming the same swappable group? You can just write them side by side, and you will see that the absolute difference between the adjacent chain should be less than equals to limit. Now when I define the absolute difference between the adjacent chain, then you might feel that 11 and 8 is having a difference of 3, but you can always rearrange it to get 11, 10 and 8, or in any other way to get an absolute difference of less than equals to the limit value. So this will be forming a chain. Now this chain can be rearranged in any possible order, and that one I will be telling you in observation number 3 in detail. But let me just show you how. Like let's say if I have to swap this 8 with 11, then how to swap this 8 with 11? Directly you cannot do that. But since they belong to the same group, what I will do is my final output, what I'm expecting is 10, 8, 11. Let's say this is what I want to find. But directly I cannot do this. So what I will do is I will swap this 11 with 10, and I will be getting 11, 10 and 8. And now I will be swapping this 8 with 10, and I will be getting 11, 8 and 10. And then I will be swapping this 10 and 11 to get 10, 8, 11. So I have reached to this state from the initial state in certain number of hops. Yes, it may take more than one hop, but it will always be possible to rearrange the group of items into any possible arrangement that you want to make it. And therefore, it will always be possible to also make it in the lexicographically smallest value arrangement, right? That I will be showing you in observation number 3. So how to know if certain items are actually belonging to the same group? Well, you have to sort this entire array. If you sort this entire array, all the groups will come together. Because if you look at it, this 10, 11 and 8 are forming a group because the adjacent chain difference will be 2 if you reorder them in some way. And this 3, 5 and 2 will actually form together a second group, right? Therefore, once we have identified these two groups, the swapping will only be possible within the items of the group because of the limit constraint, right? So swapping is only possible within the indices of the group elements. So our goal will be to find the groups with the respective indices, because if you don't mark the indices, then how will you know where to swap? You cannot just swap anywhere, right? You have to always remember that in group number 1, let's say for group number 1, this 10, 11 and 8 belong to indices 0, 3 and 5. So that whenever you have to swap this, let's say 10 and 11, then you will be swapping it in the original array, knowing about the indices where to overwrite it. So if 11 has to come to 10's place, then 11 has to be coming at the index 0, right? So the index has to be remembered. So find the groups with the respective indices, and then we have to order the items group wise. This should be the goal, right? and we should always remember that simple sorting won't work because of the limit swap constraint. This is observation number 1. In observation number 2, all the group elements will always occur together. This I already said. So if you just sort them, all the group items will come together. So I have given the same example with the limit value 2. If you sort them, then you see the group 1, 2, 3, 5 is occurring together, 8, 10, 11 is occurring together on the other side, right? You may have more than 2 groups as well. You may have 1 group also. I already told you that you have to also maintain the indices, because that is how you will know where to swap, because I cannot just sort it and give it as a result. I have to exactly know where they are to perform the swapping, right? So this is observation number 2. The third observation will be whenever you have identified a group, let's say you have identified 10, 8, 7, 5, then it will always be possible to rearrange a group in such a way that it will be sorted. And you know that whenever you have a group of items like 10, 8, 7, 5, then you will always want it to be arranged in the lexicographically smallest ordering. And if you sort these items, then it will always give you the lexicographically smallest ordering, that is 5, 7, 8, 10 in this case, right? So my final goal would be to always identify the group and mark their original indices. So the original indices of this 10, 8, 7, 5 must be stored. So this will be 0, 2, 4, 5. And then you sort these items. So you will get this sorted set of items. And now you already know the indices at which they are placed. So you have to place all these items left to right. So 5 should be placed here, 7 here, 8 here, 10 here, right? So the ordering can be known by capturing the items and sorting them, and the indices will be captured by a separate array maybe, right? You have to track all these things. So as I had already shown you in the observation number 1, that if a group is present, like let's say you have identified 10, 8, 7, 5 to be the group, you can rearrange them to always arrive to the final state of the sorted array. You can just rearrange them in any order. So in this case, in order to arrive from 10, 8, 7, 5 to 5, 7, 8, 10, I have shown you a set of steps. So in this case, 5 and 7 will be swapped, and then you get to this state number 2. Then again 8 and 7 is swapped. We will reach to state 3. In this case, swap 7 and 5 because the limit value is 2, right? That is why I am not directly swapping with all the items. And then you reach to state number 4. Then again, likewise, you keep following. Swap this 10 and 8. And then swap this 8 and 7, then swap this 7 and 5, and then you will get to the final state of the sorted set of items. It will always be possible to do that for a group. So having seen these 3 observations, we can solve this entire problem by following a 2-step process. And the first step is to get the ordered group with the indices. Now you know why you need indices, right? Because you have to track the group items where they are present in the original array. So given the original array, let's create a copy array. So this copy array will be having a pair of items. The first value will be the actual value from the array, and the second value of the pair will be the index, the original index which where the item is present in the original array. So if you just move left to right and just capture it, make a new copy array. So this is an extra space, right? So in this case, 10 is present at index 0, 3 is present at index 1, and likewise I have entered all the elements in the copy array. After that, I need to bring all the group items together. So I will be sorting this entire array based on the value. So I have sorted it, and you will find that the yellow items fall in the group 1. Okay, because the adjacent chain difference will be always less than equals to the limit value. In this case, the limit value equals to 2. So you will find that the first and the second item absolute difference is 1. Second and third item absolute difference is 2. But if you look at the second and third item, then the absolute difference will be greater than 2. And that is why this is where the group is breaking. And hence the next group will start, and you just have 2 groups in this particular example, right? So this is how we will maintain the indices of all the items. We are preserving the original indices, and we are also sorting it to identify what all elements fall into the groups, right? So we are clearly defining the group here. So sorting brings the same group items together, and the indices help identify their actual location in the input array. So this is very important. This is step number 1. Once you are done with this, then we have to move to step number 2, where we need to order the items. So from the original array, I have got the copy array which has been sorted, and the limit value is 2. So I will just apply the two pointer approach to build the final lexicographically smallest array. Okay, and how to do that? So in this two pointer approach, what I do is I will be taking the left pointer and a right pointer. So the right pointer will continuously move to the right unless we find that it is moving out of group. So how do you identify that the right pointer has moved out of group? Well, the right pointer will always be comparing with the previous item, and it will check the absolute difference between the current right pointer and the previous item. So if the difference is less than equals to limit, then we are within the same group and the right pointer will keep moving to the right. So 3 minus 2 is 1. Okay, absolute difference is 1 and it is within the limit. So yes, these two items are in the same group. 5 minus 3 is 2. So it is within the limit. So yes, the right pointer can move ahead. 8 minus 5 is 3, which is not within the limit. Therefore, the right pointer will stop here. So at this point, all the elements until the index right minus 1 will fall into the first group. So this is group number 1. You have identified that. Now in group number 1, you exactly know what are the items. So using the I pointer or any other pointer, you can just iterate over all these items. So you will get 2, 3, 5, right? So you will get 2, 3, 5 as the items. And what are the indices? It is 4, 1, 2. So you will get 4, 1, 2 as the indices. So you exactly know where these group items are present, 4, 1, 2. Now in this copy sorted array, if you move from left to right, you already know that these items are the lexicographically smallest in the group. It is already arranged in the lexicographically smallest order because you have applied sorting on the original array, right? So I don't care how the values are written in the original array, but I know that whatever is present in the sorted array must be the lexicographically smallest one. So that is why I will just be overwriting the values by moving from left to right. So if I have to do that, then at what index this 2 should be present? This 2 should be present within the leftmost index of this set of indices. So how will I find the leftmost index? Either you iterate over it and compare and find, or otherwise you sort the indices. So if you sort the indices, I think that makes sense. So that will become 1, 2, 4. So place 2 at index 1. So overwrite this to 2. Then you go to the next value, which is 3. Okay, you go to the next value, which is 3. So place this 3 at index 2. Okay, you go to the next value 5 and place this 5 at index 4. Fine. This is how you will do the rearrangement in the lexicographically smallest possible order for the given group 1. And now you can just update this left to here. I mean, you could have just iterated using the left pointer, but I will not do that. So you can just update the left pointer to the right and make right plus plus. And now again repeat the same process. So compare this right with the previous value. The absolute difference is within the limit. So this is in the same group. Compare this 11 with 10. The absolute difference is within the limit. So it is in the same group. And when the right is falling out of bound, then definitely we have to stop, and everything from L to R minus 1 fall in the same group. Again you repeat the same process. What you have to do? Again you have to just take out the indices 5, 0, 3, and you know that these are the indices at which the group items are present. So you need to sort the indices. So you need to sort all the indices. So you will get 0, 3, 5. So you exactly get the left to right ordering of the group elements. And this sorted copy array is actually telling you what will be the lexicographically smallest arrangement for this group. So 8 should be present at index number 0. So place 8 here simply. Then 10 should be present at index number 3. So make 10 here. And then 11 should be present at index number 5. So place 11 here. Right, and we are done. We are done. Update this left to this right value and we are done. Make right plus plus. So right should always be less than, and we are done. Now after doing this entire operation, what is our final array? It is 8, 2, 3, 10, 5, 11. So this will be the lexicographically smallest array that we can build from the original array given the limit constraint. Okay. So in this particular solution, the most time taking step was to do the sorting. So order of n log n was the most time taking approach, where you were creating the copy sorted array, because after doing that we are just iterating each item exactly one time, and we are taking a segment, that means a group, and we are sorting it again. So if you sort segment by segment and add it, it is never going to be greater than order of n log n for sure. So anyway, the most time taking step is n log n, and the space complexity is only due to the copy sorted array, so that is going to be order of n. Therefore, you will find that the time complexity is n log n and the space complexity is order of n. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, we are given the nums array and the limit value. So I am finding the number of items. The step number 1 was to find the location of each of the number. So I will be creating the copy array and iterate over all the items in the nums array and create a pair, the item and its original index. Then step number 2 was to get the ordered array with their original index. So these two were combined in step number 1 in my explanation. So we will be sorting it so that all the group items comes together. Then in the second step, here it is mentioned step number 3, we need to find the groups and place the ordered values. So let me just bring all the code together. So in this case, as you can see that the left value has been assigned with 0 and the right value with 1. And until the right pointer is going out of bound, we will continue to process it. So I will be tracking all the position, that means all the indices starting from the left. And I will keep pushing the right until it goes out of bound, or otherwise the value difference between the right and right minus 1 is out of limit. If it is within the limit, we will continue to push the indices into the position array and keep moving to the right. After doing this, when we stop, that means the current group items have been pushed into the position array. So the position array will only be taking the actual indices, original indices, then sorted, so that we will have the indices in the left to right ordering. And after that, we have to iterate from the left index to the right minus 1 index for all the items. And then whenever we see an item A, it has to be placed at the position index from left to right ordering, as I had shown in the dry run, right? And once we are done with this group, then the left will be updated to right and right will become right plus 1, which is being done here. And we will continue to repeat the process until all the elements have been processed. And finally, we will be returning the nums array after making the changes. So this is how we will be solving this problem, and I hope you were able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.